My name's Mike Barker. I work for a company called LMAX, which is a financial exchange. We're a company that for which performance is of a fair amount of importance. Latency is certainly one of the criteria that some of our customers look for with us. So we tend to do a lot of research especially into concurrency, because it seems to be one of the hot topics in performance nowadays. And certainly one of the things I've discovered over time is that I really hate locks. So I'm going to give you a talk today about not using locks. To give an example, one of the open source projects that we launch, and I'm the current maintainer of, is the Disruptor, which some people may have heard of. The only place that we use a lock inside of the Disruptor is to use a condition to signal another thread. We don't do any memory protection or data protection using locks whatsoever. It's all done using non-blocking constructs. So what is a non-blocking construct? Well, that's what I'm going to talk to you about today. So we've got 50-odd minutes to go through that. The other reason that I really wanted to talk about non-blocking concurrency is I believe, and this has seemed to be echoed anecdotally from a few people I've met and talked to, that I believe concurrency, especially in sort of places like universities and certainly in most of the material, is taught completely wrong. I think people should be learning non-blocking concurrency first, not last, which seems to be the general approach. People seem to say, right, first you start off and understand mutual exclusion and locks, and then we do all the really advanced stuff with non-blocking concurrency, where we introduce memory models and visibility and ordering. I think that should be flipped around. To give you an anecdotal quote, a former colleague of mine, a guy called Martin Thompson, teaches a course in high-performance concurrency. And this is sort of being taught at things like high-frequency hedge funds, people building messaging systems, that sort of thing. And in teaching this course, one of the observations that he has had of the developers working on concurrent code is that generally, he basically takes a set of exercises which are implementing specific concurrent algorithms and structures. And he finds that generally with only just a little bit of help, nearly all of his attendees, which are normally pretty top-notch developers, can solve the problems using non-blocking concurrency reasonably well. When it comes to using locks, it all falls apart. And actually, many of the problems are better solved and easier to solve if you think about them from a non-blocking perspective, especially when you have somebody giving you the terms and the underlying primitives and an explanation of how things work. The other interesting side is actually a lock is significantly more complex than any of the non-blocking primitives that I'll talk about today. It's actually built up of them, and also requires very complex coordination between the underlying hardware to give you the appropriate instructions for visibility and ordering and all these sorts of things. Complex coordination with regards to the operating system, because it has to handle parking and unparking of threads and context switching and all those very complicated operations. And your own business logic or your own code in order to interact with those services. So actually, a lock is one of those things, it's like an iceberg. There's a little tip which you play with, but actually there's a big sea of stuff that happens underneath. And this is what you often find if you ever do any performance work that's parallel or concurrent. You'll often find that the biggest points of pain, or certainly the performance bottlenecks, are when you're running into contended locks. So I'm sort of going to say, that's about all I'm actually going to say on locks themselves, and I'll spend the rest of the time talking about non-blocking concurrency. So rather than slagging locks off all day long, which I could do, which I'd like to do, I'll talk about some of the more interesting stuff. So the interesting thing about some of the primitives that you use for non-blocking concurrency is they're really just artifacts of the CPU, and the CPU exposing its own memory model up to you. And I'll talk a little bit about what a memory model is and why we need one in a minute. So first, we should be starting at the bottom, the CPU. So this is sort of a rough sort of schematic diagram of bits of the Intel Sandy Bridge CPU in particular. So this is reasonably modern. Ivy Bridge has sort of subsumed this, but the architecture is roughly the same. Not till they do Haswell, where we actually get new architecture. But it's interesting to look at all the different parts that you have in a CPU. They're actually hideously complex. And there was a talk earlier today, the keynote, which Steve Paul mentioned that this massively increasing transistor budget, doubling every year to 18 months or so, and it all gets spent on stuff. And what often happens is you don't get more gigahertz, but what you tend to get is larger caches and more execution units and greater inline parallelism and bigger buffers and all that sort of thing. So just to give you a quick sort of walk through the general CPU and sort of some of the important bits here. So obviously we have instructions at the very top. We have instructions feeding in, loaded up from memory, running through the system in order. They basically get decoded, and then we get various loads and stores placed in various other buffers, and we do a bit of branch prediction and try and analyze what particular instructions we want to do and ones that we don't want to do. But they're pipelining up. But then, if you notice, there's a little line in between, in the middle of this diagram. It's got in order and out of order. And this is one of the most interesting aspects of modern CPUs, is they're allowed to take your code and run it in a different order, based on some certain constraints, and I'll talk about those in a minute, but they can actually start executing things not necessarily in the same order that you fed them into the system, or even or the way that you wrote them in your code. And the reason for that starts to come down to these boxes along here. So these are effectively different execution units. So you've got instructions feeding in, you've got a scheduler trying to decide where it's going to send its various instructions. And then you've got these execution units doing various different actions. So we've got a multiplier over here, a divider over here, an add unit here, a jump unit here, some load and store execution units, some more store data execution units. So the thing is, if you had, for example, a store instruction, or let's say you had a store instruction, you had some arithmetic straight after that. Well, it would really like to be able to send the store instruction in and continue on doing some arithmetic at the same time. But those instructions might finish at different times as well, so you want to sort of let things flow through to memory. But because you've got this increasing complexity, and this only happens to be Sandy Bridge, you've got lots of other processor architecture, Spark, Alpha, all sorts, and they all do things a little bit differently. But we don't really want to have to deal with this in detail in our own code. So we don't really ever sit down, write our code and go, well, I know I've got 6 execution units on this particular CPU that I'm going to deploy to, so I'm going to line my code up this way, and I understand that this one's going to probably happen first, so I need to understand what will become visible in another thread. The idea is not to try and worry too much about the underlying architecture, but why the architecture is there to give us something else, which is essentially a memory model. So memory models are exceptionally important, and they're basically your #1 tool when doing non-blocking concurrency. And the purpose of a memory model is to sort of allow hardware architects to build more and more complex CPUs that do more and more out-of-order execution, more and more branch prediction, speculative operations, that sort of thing, but still giving the developer something that they can reason about. So a memory model is essentially an abstraction over hardware, and to a degree your compiler, so that you can actually reason about the behavior of your code in various conditions. And this becomes much, much more important when you're talking about concurrency. So Java is really interesting. Around Java 5, Doug Lee and a few others, can't remember all their names, introduced the Java memory model. And this actually was pretty forward-thinking. It was actually one of the first mainstream languages to set forth a full memory model for what happens in the various concurrent situations. And it's a quite well-defined model, and it's quite interesting. They managed to come up with something that actually works pretty well across most sets of hardware. Gives you quite decent, still gives fairly decent optimization opportunities to the compiler authors, but also gives the developers something decent to reason about. We had a bit of an argument between a few of us about whether you could consider the Java memory model a strong memory model or a weak memory model, sort of stuff. For example, it's a lot weaker than the x86 memory model, so CPUs have their own memory models as well. I'll show some examples of that in a minute. But what are the things that the Java memory model allows? So there's one sort of main concept that is at the core of the design of the Java memory model, and it's what's called, it's a bit of a mouthful, it's called, this Java memory model provides serial consistency for race-free programs. So the idea is that you have no races. If you properly fence your code, it will basically exhibit as serial-style consistency. So what that disallows is things like some values just magically appearing out of thin air, for example. You can't just read a value and it just magically happens to be something that's unexpected. There should always be a reason for that value turning up. It's interesting, this is ahead of the C and C++. C++ only just last year added a memory model. C, I think, is probably going to add one this year. So when you're programming in C and C++, if you're doing some advanced concurrency stuff, it's almost impossible to reason about your concurrent code across multiple architectures. it takes a lot of testing and a lot of specialist assembler in many cases to get C and C++ programs concurrently correct. So this is, I think, one of the biggest advantages for programming in Java, certainly in a high-performance space, is that you actually have a much stronger memory model that's a little bit easier to reason over. You only have to Google for Linus Torvalds and GCC to look at some of the complaints that people have about what GCC does to code that makes it almost impossible to do concurrent code in C. I have heard similar comments from some of the guys at Azul, even to the point where they actually use multiple compilers to compile the Azul platform, because GCC occasionally just makes a whole mess of the ordering of the instructions. So one of the first constructs that is very, very useful in the Java memory model, and this is the main one to remember, is what's called happens before. So the idea being is that you can reason about the order of instructions on your system, not from the idea of a total order, which is every single instruction is ordered relative to every other instruction, but give you an idea of a partial order over your code. So you can say certain instructions, if they happen in this order, the instructions around them will also happen in the same sort of relative order. It sounds a bit of a mouthful, but it's a little bit easier once we start looking at an example. So this is the idea. We've got 2 threads running away happily, and in thread number 1, I assign a value into an array. So at index 5 in my data, I assign the value 10. That's a store, funnily enough. And then straight after that, I then assign the value 5, which happens to be the index into that array, to a volatile variable called sequence. So under the Java memory model terms, this is known as what is known as a store-release edge. So store-release basically means that no other writes occurring in that thread can be reordered after this one. So because this write to memory happens before this volatile write, happens before the store-release edge, it will have to stay in this order. You know, the compiler, neither the compiler nor the CPU is allowed to reorder those two things. So on the other side, we load this value. So we basically, into our local variable A, we read sequence. And because sequence is a volatile variable, this is what's known as a load acquire barrier. And so this particular type of edge, what this means is no other reads can be reordered ahead of this particular read. So this essentially is correct. So I can say, right, I've put some data into memory. I've stored my index to that in a volatile variable. I've read that out, and I can then check to see if A equals 5. So if this happened after this one, so I saw the value 5 in that variable, then I can now read the value of data at index 5. If A equaled 4, so it's perfectly legal for this instruction here to occur sometime before this volatile sequence value, but it should return a value that's not 5, like 4, and then this wouldn't execute. But if this value here is read, matches the value here, this flow is essentially correct. So the idea is saying that if A happens before B, and B happens before C, and C happens before D, then A happens before D. And that's basically it. And there are a number of constructs in the Java system that provide these load acquire and store release edges. So store release happens when you exit a lock. Load acquire happens when you enter a lock. There's CAS instructions as well. Anybody want to take a guess? Anybody used atomic integer compare and set? Yep. Anyone want to take a rough guess as to whether that's a store release or a load acquire barrier? Anybody ready to take a guess? No? It's both. If you have a look in the Java code, effectively it's both. Because it's doing both an atomic read and an atomic write in order to do it, because it's basically saying, set this value if this other case is true. So it's actually got to do both an ordered read and an ordered write in order for that to complete. So the rather interesting aspect of happens before is it's not enough. There is another feature of the Java memory model that actually you don't really need to think about a whole lot if you're like me, who's a concurrent library author, but you do need to worry a lot about if you are a compiler developer, and that is the notion of causality. Causality is it's an interesting concept, but basically it's one of these ones that's very easy to understand intuitively, but it's kind of tricky for somebody like me to try and explain it. But what it means is that if a particular, let's say a write to memory, is inside of some condition which is based on a read from memory, then those two things can't be reordered. A good example, let's say I read a value into a local variable a, and I check to see whether a is greater than 0. And if a is greater than 0, I then write a value to memory. Those read and writes have a causal relationship. The write to memory is caused by the read, in effect. So anybody who's writing a compiler for Java can't reorder those two instructions, or they'd have to use the appropriate fences on the CPU architecture that they're using to prevent those sorts of instructions being reordered. And it seems a kind of a counterintuitive thing to ever actually run into that case, but you can imagine some really, really freaky hardware or a strange compiler might go, well, I can see that right, and I'm doing a bit of branch prediction, and actually most of the time that always evaluates to true, so what I'm going to do is I'm going to speculatively write that value in, and then if the thing returns false, what I'm actually going to do is reverse the value out. But that value might appear in another thread. This is where you're starting to get out of thin air values. It's not allowed to do that. It can't allow that sort of behavior to happen. But basically what it means is it doesn't do things that would really, really scare you. If not having causality would actually prevent quite a lot of the sorts of reasoning over your concurrent code that you'd potentially like to do. And it got me the opportunity to put the Star Wars quote in there. Other memory models. So this is going to be relevant in a second because I'm going to talk a little bit about concurrency primitives. But I wanted to mention as well, mentioned recently that CPUs have their own memory model too. So this is the complete set of rules for the Intel x86 memory model. Has anybody read the Java memory model spec? Which one's simpler? So to give you an idea, this is what some people call a much stronger memory model than the Java memory model. It's actually, when you look at December, it's actually quite easy to reason over. But a couple of the highlights are reads are not reordered with other reads. If you do a read and then do another read, the CPU won't reorder them. You do a write and then do another write. The CPU won't reorder that either. Stores are not reordered with older loads. So if you do a load, then a store, it won't move the store ahead of the read. Memory ordering obeys causality. There's that causality question coming in, causality point coming in again. Stores the same location have a total order. That means all of the stores you can order completely across your system. The other one that's very interesting is in a multiprocessor system, locked instructions to the same location have a total order. So this is quite a useful tool. Locked instructions turn up quite often when you want to do various sorts of memory fences. We'll see that in a minute. And then loads and stores are not reordered around locks either. I actually kind of like reasoning over this. I find this a bit easier to understand than the Java memory model, but I've sort of managed to get my head around it. So the next thing I wanted to talk a bit about, and give a bit more detail, about what are the tools? What tools do you have inside the Java to deal with non-blocking concurrency? Well, there's kind of three-ish. The first one is volatile variables. Like I mentioned earlier in that example, stores and loads from volatiles give you your store release and your load acquire barriers, as well as a couple of sort of a full memory flush as well, and I'll talk about that in a minute. The other set is all the stuff under Java util concurrent atomic. So that's your atomic long, your atomic integer, your atomic reference, and also the associated atomic integer array, atomic reference array, and atomic integer field updater. Has anybody actually tried using the field updaters in their code, ever? No? Yeah. It's an interesting aspect. Here's a quick question. If we have atomic longs, atomic integers, and atomic references, a bit of a performance question, why would we have also atomic integer array? Couldn't I just create an array of atomic integers? Why have I got atomic field updater? Anybody want to take a guess? Nope. Basically, it avoids an additional dereference. So if you're writing concurrent code like this, you're probably going to be focusing on performance. So having to do an additional dereference to another object in Java, potentially a cache miss, all that sort of thing. So the atomic reference arrays, if you've got arrays of stuff that you want to make concurrent, definitely use those, because you actually use the same effective storage. It's just going to make sure the appropriate memory operations happen when updating the values in that array. Similarly, for atomic field updaters, what they do is allow you to not have to have a separate object that you're going to have to dereference to do your atomic store. You can just have a variable, and then you can allow the field updater to change the same variable in your class. So it just prevents an additional dereference and potentially a different cache miss and all those sorts of things. There is one other concurrency construct that does non-blocking concurrency as well as a lot of other things. Does anybody know what it is? Martijn and Kirk talked about it yesterday. Anyone has a guess? The unsafe. So basically, if you actually read through the concurrent libraries inside of Java, they all call down to unsafe. So unsafe is basically a tool that allows you to modify memory in particular ways to enforce these various barriers, these ordering barriers, load, acquire, store, release, that sort of thing. The general impression with unsafe is it's a bit like Fight Club. The first rule of the unsafe is you don't talk about the unsafe. And to be honest, if you're smart enough to use it, you probably don't need me telling you how to use it. And if you can't figure out how to use it, then you probably shouldn't be using it. So much to say, it's a bit like this. You know something bad is going to happen, but it's not the monkey's fault. So, as I mentioned before, so various concurrency constructs. I'm going to have a look at a few of them. So I'm just looking at the source code for atomic long, but I'm going to go through a couple of ways that you can actually make specifically writes, because these are what's really important. Reads in non-blocking concurrency are fairly straightforward. You just have to make sure to do a volatile read, and it's fairly cheap on most platforms. It's when you start to write and update data that things become more tricky. In fact, I have a thesis that if you never had more than one thread ever trying to write to any location or ever try and write to any one resource anywhere, the only, concurrency construct that you ever need is the volatile variable. All the rest of them are to deal with multiple threads trying to access the same data or trying to write to the same data. So I'll talk a bit about some of the interesting challenges around that in a second. So very basic one, volatile write. So basically you do a set, and this is just looking at the internals of the atomic long. You do a set on your value and just assign it to a volatile long. The assembler for it. So what does the system do with that? What does the compiler do with that? How does this actually get implemented within the underlying CPU? Well, there's a lot of boilerplate there. Anybody who thinks that Java code's got a lot of boilerplate should try some assembler sometime. So this is the assembly code that's generated for atomic long once you disable the inlining. And you'll notice that there's a whole bunch of stuff happens, and then there's this move instruction. And directly after that move instruction is the lock add. So what would happen is if I was setting something and then I was assigning a value to my atomic long in order to give me this ordering fence, this would be ordered afterwards because we know from the x86 memory model that my stores are not reordered with respect to other stores. But this one here is interesting, this lock add long. So basically saying this is a lock instruction. So this lock instruction inside of Intel will do a couple of things. First of all, it'll basically flush your entire pipeline. So it basically stops any new instructions getting to the CPU. So it flushes that pipeline of instructions, it flushes all your store and load barriers, and waits for all the execution units to finish all the work that they're doing. Then allows the instruction through, and then allows the rest of the instructions to continue on afterwards. And we'll see some of the performance impacts of that in a bit. What it's doing is basically doing an add of 0 to the stack pointer. It seems a bit odd, but basically it's a no-op. But because we've enforced it with a lock add instruction, it's basically giving us this full memory fence and helping prevent this reordering effect, but also giving this full flush out to memory. Here's another interesting one, another pop quiz question. Anybody know why particularly it's adding 0 to a stack pointer? Imagine you've got multiple threads running in a system. Multiple threads writing to volatile variables. How, and if you were at Martijn and Kirk's talk last night, they talked a little bit about false sharing and how volatiles effectively, if you're writing to a volatile variable, you're actually not writing that value, you're writing a whole cache line. So if volatile variables are too close to each other in memory, you get cache misses. This is, I'm assuming, I don't know this for certain, but I'm assuming the stack pointer is used So there's a very, very low chance that you'll get any form of false sharing. So it's very unlikely that two threads are going to have their stack pointers very near to each other in memory. So it's I think this is a bit of a trick, performance trick, to make sure that we don't end up with false sharing when writing a volatile variable. So another one. This is an interesting one, lazy set. So here's the unsafe being used internally inside of the atomic long class. Lazy set's a slightly interesting one. This is something, if you do decide to use it, be a little bit careful with, because it's not actually specified in the Java memory model itself. There is rumors of a Java memory model revision coming at some point in the future. So whether that's for Java 8 or 9 or 10, I'm not too sure. And they'll include this. And this has very, very similar ordering semantics as to volatile variables, but it's a little bit faster. Why is that? It emits a lock instruction. So all of this lazy set does is it doesn't do the full flush of all the pipeline and all that sort of stuff and give you all the total ordering benefits. All it does is just make sure that your instructions don't get reordered around it. That's all it does. So you can get some additional performance benefits by using lazy set. But obviously, test, I did run into a bug in not the hotspot JDK, but a different JDK, using a lazy set with an atomic field updater. Oddly enough, actually, I switched to using the unsafe, and the bug went away, which was kind of odd that the standard API didn't work and the undocumented one worked really effectively. And the third main one is one we talked about a little bit earlier, is the concept of compare and set. So again, you can see internally it actually uses the unsafe. So cas is a really interesting instruction. It's quite important. And it turns up whenever you start getting into this problem of having multiple threads write into the same piece of data. Because basically you need to atomically update something, but you want to make sure nothing else has come in and updated that thing at the same time. I'll give some examples of how this is used in a couple of slides. There's something else I was going to say on that, and I've forgotten. So have a quick look at the assembler for that. So this is the compare and set argument, compare and set method compiled into assembler. And you'll notice that we have a different instruction here now. So this is a specific Intel instruction for doing this particular operation. Most CPUs have something very similar to this to support this compare and set notation. PowerPC has, I think, something called linked load store conditional, something along those lines. Intel actually has a whole raft of lock instructions. They even have things like lock XAD and things like that, so you can do conditional additions. The lock compare and exchange will basically try and do this update, but what will happen is if it fails, it will return you the old value and won't let you update it to the new value. So you tend to write these things in a loop, saying loop until I can actually write this thing in and it succeeds for me. But in Intel, you can actually do a couple of things where you say things like lock XAD, which will actually atomically add a value to a place in memory. And in that sort of case, you won't need to have a spin. It'll just sort of basically queue any particular writes going to that same particular location. So these obviously going to have varying performance impacts, especially with these lock instructions and comparing it to lazy set. So basically just trying to, just at a very simple performance test of them writing over the same piece of memory. And you'll see this is nanoseconds per operation. So a compare and set and a set, so using a volatile variable, around about 8-ish nanoseconds for an individual instruction. This is completely uncontended. I wouldn't read anything into the difference between the set and the compare and set. I think it's probably just experimental error. And certainly, this was uncontended, so it was only one thread trying to write down. If there was two threads doing compare and sets, you would probably find that with the sort of the back-off retry loops that end up being run, that this would become slower. So don't somebody go running out. So cas is faster than volatile writes. I should use that everywhere. So don't read too much into that difference. But you can see when we remove the lock instruction and just apply that very, very soft ordering, saying, I just want to make sure my instructions don't get reordered ahead of this particular write, that actually your performance increases significantly. The other interesting aspect, which I haven't got a lot of slides on, but is when you start talking about false sharing impacts are much, much lower, because when you do a lazy set, the CPU is able to do things like write combining. So it actually sees two lazy sets to the same cache line, and it just puts them together into the same write and passes them off to memory. Whereas if you're doing it with volatiles, it has to put memory fences in between each of those two writes. and potentially you've got lots of horrible change of ownership requests floating backwards and forwards between the CPUs. So yeah, interesting optimization if you do have a very simple algorithm, and when we do in the Disruptor, lazy set can actually give you some big wins in terms of performance. So what I wanted to talk about now was actually designing a non-blocking concurrency algorithm. So this is a particular problem that we ran into with the Disruptor, and I'm now on to my third implementation of a non-blocking algorithm to solve this problem. And this is basically the only point that we have the only point of contention we have inside of the Disruptor is when you have multiple threads want to publishing into the same ring buffer. So it's a fairly common problem. Think about I've got a Disruptor sitting there. It's going to be dispatching events over multicast to another service, and I've got a web server with 200 threads, and they're all writing into the same ring buffer. It happens. You know, you basically want to have some algorithm to efficiently deal with all these multiple producers writing in at the same time. So I've written a bit of a performance test on the various algorithms that we've tried and show you sort of the implementation, the sort of problems they were trying to solve, where they sort of fell apart, and actually the relative performance of the various algorithms, and how we got to the solution which we currently have, which I think is very, very elegant. So this is the basic algorithm within the Disruptor. So the Disruptor has a multi-stage process for putting data in. So the first thing you do is you call next and give yourself a slot in the ring buffer. You then use that, and I've just done a very much simplified version of the full Disruptor. Basically, we're setting a value given the slot that we've claimed and the value we want to stick in. And then we make that available to all the reading threads via a call to publish. This is the way you access the Disruptor. Version 3, we're actually going to try and hide a lot of this from you because this has all sorts of potential failure cases. What happens if set value fails with an exception? You end up with claiming a slot that's never published. So take it with a grain of salt. But that's the basic flow that you're doing with inside when you're putting data into the Disruptor. So you've got multiple threads coming in and trying to do, give me a slot in the ring buffer, set that particular value, then publish. And you want to make sure that the values are published to the consumers in the exact same order that they're claimed. So we don't want to publish the value 50 before the value 49. So we don't want the consumer to see those are things pairing out of order. Certainly the business logic downstream. We want to maintain that order absolutely. So the first algorithm we ran with. So this is the implementation of next, and we use this implementation in the first two algorithms. So the simple thing we do is we have two sequences in our ring buffer. First thing is we call the next sequence. This is the next sequence I'm going to issue. And we have another one called a cursor, and you'll see where that's updated in a minute. So the first thing I do is I get the next sequence. I get the current sequence. So I get where it's currently at, and I add one to it, because this should be the next one in the list. I then check to see whether I've wrapped. So basically, I take the current sequence of the reader, I add the size of the buffer to it, and I make sure my value, if my value is greater, then I spin, basically, until the read sequence is caught up. So this is just a little bit of a condition to make sure I don't wrap over the ring buffer while the person's reading from it. If this is successful, I fall through this loop, and basically I do next sequence, compare and set the current and the next. So what this means is that if somebody else has come in the meantime, they've both got the same current value. The first thread manages to increment next, and this succeeds. The second thread will come through and try and do this compare and set, but the current value won't be the same as the one it read earlier. So this particular thing will fail. It'll just run through the loop again. Claim the next sequence, add one to it, claim the current sequence, add one to it, and then try again. So you've basically got multiple threads trying to compete to grab elements out, or basically grab sequences out, and ensuring that they're unique, and then no two threads end up with trying to write to the same slot in the ring buffer. Publish. This is where it gets tricky. This is the bit where we need to maintain the ordering of publication once we've finished filling up that particular entry with data. And this was our first implementation. And what this does, it says, oh, okay, I want to publish my sequence now. So I've got 3 threads. They've all come in, they've claimed slots 0, 1, and 2. But thread number 2 has finished its write into its sequence, into its particular slot in the ring buffer, and it needs to publish it out. But obviously I can't publish 2 yet because 0 and 1 haven't been published. So what it does is it takes its own sequence value, subtracts 1 from it, and then just spins until the cursor is equal to the sequence that's 1 less than it. And then it can basically do a lazy set on the sequence, updating it. So basically what's happening is these threads are coming in, wanting to publish their values, and they just spin until the values increment in a strictly ascending manner. Can anybody see a problem with this code? I'll show you the performance results. So I've got 5 threads. I've got a number of producer threads and a consumer thread reading from it in my benchmark. So when I start off with a single producer and a single consumer, that's 2 threads running. This is on my 4 CPU laptop. Does pretty well, 25 million, nearly 25 million operations per second. That's no good because this is a multi-producer algorithm. I want to test it as my number of threads increases. 2, it starts to decay. 3, it goes back up again. I'm probably going to put that down to experimental error. And then it starts to degrade when we hit 4 producer threads. So this is, we're starting to get more threads running busy on my system than I have CPUs. So my CPU's starting to thrash. It's starting to run out of resources to service all these threads. So you start to see a significant drop. What's really interesting is as we go further, we don't get any results at all. Basically, it ran and ran and ran and ran, and eventually I had to give this talk, so I ran out of time. So I killed it off and basically assumed I just wasn't going to get any results. I turned down and down the number of iterations to try and get it to work. Once I did that, I got very weird values. The numbers would jump up to billions and all sorts of really, really weird results, because I think what was happening, if I made the number small enough, you get one thread would basically do all the iterations it need to do within its quantum and never actually contend with any other threads either. So you got some really weird results. But basically, once you upped it to some sort of reasonable number of iterations, you just couldn't get any results at all. And this was actually found by a user of Disruptor. It was posted on the Google group, and I did a blog post about why this is so bad, and the implementation of our next algorithm. So this is the second one we tried. This one is a little bit more complicated, I think. Probably about 4 times the lines of code and about a zillion times the complexity. So the way that we tried to get around this is to try and reduce this contention, try and reduce the amount of spinning that these individual threads are having to do in order to allow these values to update. So we created a second ring buffer in front of the first ring buffer, which we call pending publications. So the first thing it does is it just makes sure it doesn't wrap the pending publications buffer. When I set this up, what I would do is normally put a logging statement in there and just basically try and tune this, set the size of that pending publication buffer so we never actually wrap that. So that's just a bit of a spin to make sure we don't wrap the pending publication buffer, and we'll sort of spin until that becomes free. But the really interesting bit starts here. So what I do is I take my sequence and I subtract 1 again and say, this is my expected sequence. And then I take my sequence, and in the pending publication buffer, I basically set my sequence. So this is basically a modulo operation. So the index in the pending ring buffer, I set my value in there. So I say, my value is set in the pending ring buffer. It's now pending for publication. I will then check the current cursor value. If the cursor has already reached my sequence value or greater, somebody's already published my sequence for me. So I can just exit. I don't have to do anything more. I can just return. If that's not the case, I grab the next sequence. Then I start doing this. I basically do a compare and set with the expected sequence, the one I subtracted 1 from earlier, with the next sequence, which is my sequence in this case. So I'm basically doing a compare and set to say, right, I'm going to take my value and the value expected and publish it. The interesting thing here is most times when you see cas loops, like the one we showed on next, most people do a retry on failure. In this case, I flipped it round and did a retry on success. So if that fails to occur, what it basically means is that because my expected sequence was strictly 1 less than my current sequence, and sequences are only going forward, it means my sequence must have been published by somebody else. Somebody else must have hit the same piece of code and published my sequence for me. So there's no point in me trying to do anything more. I just exit again. But if I succeed, what I do next is go to the pending publications list and try to continue. So I try to continue publishing other people's sequences. So basically, I call this algorithm co-op. So basically, threads are sort of cooperating together to publish each other's sequence. This has the nice effect of if one particular thread has pushed another one off the core, it didn't manage to publish its own value, the currently running thread can just publish a whole lot of values for it. So the idea is rather than having threads stop and spin and wait to do the amount of work, they basically try and publish stuff, but if they can't, they just let somebody else do it for them. So how does that one fare? Well, it fares a little bit better. So when we're down, because of the additional complexity in that algorithm, certainly at the single CPU level, it's not nearly as fast. But as we add more CPUs, it gets faster and faster because we've got more messages going through our system, getting a bit of parallelism out that way. And certainly once we're getting to as many publishers as we have threads, or slightly more threads than we have cores, it's better than the old spin -1 algorithm. But once we start really contending on the CPU, it works, it keeps on going, but it does tail off. So it doesn't really scale all that well. So we're starting to fall off down to around about 10 or 19 million, then sort of down to about 6 odd million operations per second. So it's not scaling particularly well. But it is working, which is a lot more we can say than the first algorithm. So in the Disruptor version 2, we have both. And the idea is you pick which one you want. So if your number of threads is quite high, more than the number of CPUs you've got, you pick the co-op algorithm. And if you've got lots and lots of cores to play with and you don't really care about spinning lots of them, you can pick the spin -1 algorithm. But that's nasty, really. I mean, I don't want to have my users picking a particular algorithm based on what they think their hardware might look like. They could basically say, I'm going to have a multi-threaded system, I want it to work well. So we came up with the final algorithm. First is we have made a slight change to the next call. And it's very subtle, but the thing is we got rid of the next sequence. We only have one sequence on the ring buffer, we just have the cursor. No next sequence whatsoever. The interesting aspect is we increment this straight away. Where the consumer will already see, because this is the thing that the consumer looks at to see where it's up to. It looks at this cursor. So it's already seeing values being published. The interesting aspect about this one is rather than having these threads contending on the right and spinning, waiting for each other, we decided to offload some of the work for ensuring the ordering over to the consumer. The nice effect that this has is we remove a lot of contention. So what does the publish look like? Well, this is the publish method. What we do is we create another buffer, the same size. This is an array of longs, or an atomic array of longs, that's the exact same size as the ring buffer. And what I do is I set into that published value a value that will indicate that my value is ready to be read. Basically, the way it works is we have an index, we have the sequence number, we do a mask operation to give us the index into the ring buffer, and then we take the remainder of that as the value to indicate that that particular one's being read. If you're interested in the details of how that actually works and the math behind it, come have a chat to me afterwards. I'm not going to go through it here because it's a little bit convoluted. But basically, we're just marking a field in this additional array to say, this is now available. So we take the index of the sequence and the published value. The thread on the other side that's reading is basically calculating the available value, grabbing the index of the sequence, and it's basically doing a spin with a check to make sure that it has been published. So the interesting aspect here is there's now no contention at all on the publish. Whereas all the previous algorithms, they had a contention on the next, so they had to do that cas to grab out their next value, but they all suffered from when they tried to publish it, they ran into contention because they're all trying to contend on exactly the same value. What we've done here is removed all of that contention completely, but pushed a little bit of responsibility for assuring the ordering is correct to the reader thread, which is far more advantageous because reads scale much better than writes. Contended reads at the same location that doesn't change, or with a single writer, is much, much simpler and easier to do. Or certainly a lot faster and easier for the code to optimize and the CPU to deal with better because you get a lot more caching effects and that sort of thing. So, and this is quite a bit simpler. So I quite like that it's simpler and a lot more elegant and just moves the responsibility out to the other thread. And let's see how it performs. Quite a lot better. You can see as the number of threads are added, there'll be on the number of cores. The new algorithm, which I call the buffer algorithm, for want of a better name, continues to scale really, really nicely. I suspect this is going to tail over at some point, but I got bored once I got past about 8 threads running it. It exhibited the right behavior. So the idea is in the next version of the Disruptor, which is 3.0, we're going to scrap the 2 algorithms and just have the 1, which is certainly a lot more desirable for people that want to use it. So my last slide. What sucks? Stuff that sucks. There's one really, really, really big problem with concurrency today, in my mind. So this is merely my thesis. And it is, how do you wake up another thread? How do you have, I've got a thread here, and I'll pass a message over to that thread there, and it's idle, how do I wake it up? There's several ways to do this, and they're all crap. So the simple one that people tend, the one that's not simple, the one that people tend to do is they tend to use a lock and a condition. So this is where you create a lock, you create a condition variable from that lock, and then you call await if you're waiting for somebody to wake you up, and you call signal in order to wake them up on the writer side. If you're using the slightly older school synchronized keywords, you're using wait and notify. What's the problem with that? It's great. A wake up on most operating systems is between 4 and 16 microseconds. So remember we're talking about some of those operations, the lazy sets and the sets, and we're talking nanoseconds. We're 3 orders of magnitude higher up the stack in terms of costs. The other really interesting thing is this is when the operating systems get in the way. Anybody here heard of JHiccup? Seriously, if anybody does anything with performance and has any considerations around latency, look at JHiccup. It's the simplest but one of the most elegant tools you ever see. What it does is it measures the amount of time it takes your operating system to do nothing. It's a bit odd, but basically it sits in a loop, sleeping for a millisecond, and then waking up, and timing how long it took for that sleep to take. So basically it's saying to the operating system, park this thread, and then wake me up in 1 millisecond. The really interesting thing is it draws into quite a nice histogram and plots it for you. Some of those thread wake-ups can take 20 or 40 milliseconds. And that's quite a long time. And there's a huge number of things that are coming into play here. You've got things like hardware interrupts. You've got SMI interrupts for power management kicking in. You've got other daemon processes walking around. It just happens to get some sort of scheduling artifact kicking in. There's all sorts of things. So on a poorly tuned Linux system, you will get terrible, terrible results from JHiccup. It's a really interesting experiment to run on your machines to actually see how long it takes for your machine to pause you and then bring you back up again. Certainly on some of the newer kernels, like 3.3 and later, the results are much, much better. So again, when we're talking about those instructions taking nanoseconds, and now it's taking 20 milliseconds to wake up a thread, especially when you're in the high performance or low latency space, or even if you're doing a fork join algorithm. So you've got this algorithm which is doing basic manipulation of code on your CPU that can do billions of arithmetic operations a second. If you're in the process of a fork join, and a couple of your forks take 20 or 40 milliseconds just to wake up a thread to do some more work, you start to lose the benefit of that parallelism. So that's kind of one of the problems with the locks and conditions and wake-up stuff. What are the other options? Well, basically it boils down to spinning. So there's a number of things you can do. You can spin, you can do a hard spin, a very tight spin like we did in the very short cases there. You can put things in like yields and that sort of stuff. One of the problems with spinning is that, apart from the obvious, it just uses a lot of CPU, and you end up with quite a high power bill, is that it actually used to be sort of okay. I know some companies definitely do this. They just pay the money and they run the machines with flames shooting out the back because they care way more about the latency than they do about anything else, and they're quite happy to pay the cost for it. But there's something that gives you sort of a fairly poor mechanical sympathy with doing that now, is that most Intel CPUs, certainly Sandy Bridge and later, include turbo boost. So what they do is if the CPU's idle and a lot of it's cooled down and not a lot of other cores are hot doing stuff, it'll actually overclock the CPU a bit. It'll run at a higher clock rate and it'll actually run faster, which is a nice benefit for most systems because most systems have traffic that's bursty in nature. Something will happen in the world and a burst of traffic will arrive. You don't tend to get a very stable, oh, I'm always processing 200 operations per second. It'd be our system where you can get, we have non-farm payrolls in the finance organization. Now, our throughput rate jumps from 300 or 400 operations a second to 4,000 in the space of 1 second, and then it will drop right back off again. So having this turbo boost effect in the CPUs is really good, because when you get burst of traffic, and the CPU's cool, it will give me a bit more processing power to get me over that hump. But if I'm spinning hard, it can't. Basically, I'm going to heat my CPU up and take away all of those possibilities for that turbo boost to kick in. There's other tricks you can do. You can do spin with yields. You can do you can spin. Probably the only thing that gets close, and probably the thing we're going to be releasing in version 3 of the Disruptor, is some sort of phase back off. So you say, I'm willing to spin for a while. I'll spin for a millisecond, and then I'll back off to a lock, or I'll back off to a sleep, or I'll back off to, I'll do a hard spin and a spin while yielding, and then a spin with a sleep, or something like that. So that's about as good as it gets, unfortunately. One of the other toughies in Java is there's an instruction, this is specifically Intel. One of the things is if you do a hard spin is that you really need to make sure you have more physical cores than you have threads. And that's not logical cores with hyperthreading, that's physical cores. The reason being is that a hard, tight spin will actually fill up the CPU pipeline. And the way that hyperthreading works is that the two threads cooperate using those resources. So some of the operations in that pipeline will be for one thread and some will be for the other thread. But when you do a hard spin, the CPU will just speculatively execute that loop several times. And so your other hyperthread on the same core just has no resources to do anything with it all. So if you are going down that route, you definitely want to be switching hyperthreading off. Unfortunately, there is on Intel a special instruction to help you deal with it. It's called the pause instruction. If you're doing C and C++, you can just do a bit of ASM and stick the pause instruction in line. What that does is prevent that speculative execution. So you can actually hard spin, but actually have multiple hyperthreads cooperating on that. There is no pause instruction in Java. Maybe they'll add an intrinsic for it one day. Fingers crossed. There is one other way to do it, and Intel has another couple of interesting instructions called monitor and mwait. And what monitor and mwait do is allow you to pick a location in memory and an initial value, and they will wake up your process, or wake up your processor, if the value changes. Great. I can pick a C state. I can even pick a power-saving level to take my CPU down onto before it gets started up. Only problem is only the kernel can use it. It's what's called a ring zero instruction. Only the kernel gets access to monitor and mwait. So maybe one day they'll make it a user space instruction, and one day the compiler will start supporting it, one day the JVM will start supporting it, and one day there'll be a library to use it. But who knows? So I remember that circle that was drawn in the keynote, it's sort of all the way down here, we're all the way up the top. So maybe one day that'll turn up. This is my expressing the things I want from the hardware guys. So on that, I'd like to conclude. Any questions? Here's just some links. The code that I did for that performance test didn't use the disruptor itself. It used a cut-down version to make it a bit easier to demonstrate. I work for LMAX. We're hiring, so come along and see us. And there's a couple of other talks that I've given on concurrency. So yeah, any questions? Okay, thank you very much.